we also, for the software, we locate the blue LED by using either color space of red, green, blue, or hue, saturation, and luminosity. We usually combine both. We run a threshold. We've already characterized blue LEDs for what intensity levels we're expecting to see. And we run a threshold on that, which shows up objects of interest. If the objects are the correct size for how far the vehicle is away from the wall, we then indicate that that's a possible LED. To determine if it's blinking or not, we enter into a hover mode where we do a 20-second tally where it takes a series of 20 images. Through the 20 images, we define a bounding box, as you can see in the image on the left, that's the LabVIEW program running. And assuming the vehicle is not moving too much, relatively constant hover, the LEDs should stay within these boxes. We then will tally up the number of times we successfully find this. And with a blinking LED, the ratio of successful finds to unsuccessful finds will be relatively low. With a non-blinking blue LED, you will find a very high ratio. And so if the ratio overcomes our minimum limit, then we establish that as the successful LED, and then the vehicle moves in and locks onto that LED, moves in so we can read the gauge panel and send back imagery. The hardware we selected for this was a Black Widow KX141 camera, which was chosen because of its small size and it had a relatively good resolution and low light capabilities. We also used a 500 megawatt, 2.4 gigahertz transmitter. Interesting. 2.4 gigahertz transmitter, which we found when combined with a relatively powerful receiver at the base station, we could get reception up to 200 meters away. Which we deemed relatively sufficient for the competition. It was also pretty resilient to interference from other sources. We knew there might be some other 2.4 gigahertz transmissions going on. We have some of our own, and it was relatively negligible in terms of the interference we got. And now Philip will continue on with the presentation.
Okay, to discuss some of the communication systems that we have on board the vehicle, we just put in a kill switch that uses a 2.4 gigahertz RC controller that you can see at the top left. Everything on the left-hand column is on at our base station or in the judge's hands, and everything on the right-hand column is going to be on the vehicle. This is just a Spectrum RC controller with a 2.4 gigahertz radio flyer. For our video data, we're using an analog system, and as Jason said, that's the KX141 CCD camera. We just have a 2.4 gigahertz receiver, and it's transmitting at a power of 500 milliwatts. For our data communications, we wanted that to be very resilient to interference, so we decided to go with a spread spectrum extend 900 megahertz transceiver, and this is software selectable up to a 1 watt power. Here's some of the onboard power we're using. This is all for the payload of the vehicle, and there's separate batteries for the brushless motors. We're using everything at 5 volts for simplicity, and this is done by a 1.5, or actually two 1.5 amp DC to DC converter boards that we've designed in-house. And here you can see our total draw in the right-hand column. And we're at just under 2 amps between both boards. And to power these devices, we're using a 910 milliamp hour, 7.4 volt lithium LiPo battery. And this gives us a 30-minute run time for the payload. Now the vehicle will actually only fly for about 15 minutes. We've employed several methods to increase safety on the vehicle. Some of these methods have been employed during the prototype testing. And you can see our prototype vehicle on the top right. And we designed several test stands. As Jason mentioned, we had a pitch and roll stand, a yaw stand, and also an altitude stand. And these 3 stands had the vehicle securely locked to the stands through metal poles that would actually go through the vehicle. And so we didn't have to worry about anybody getting injured from the vehicle crashing. We also developed controller models before we actually implemented the controllers on the prototypes, and we're using proportional derivative controllers at the moment. We also created some shock vibration isolation, which you can see on the bottom left picture, and we just have some dampers in between the circuit boards that are on the vehicle in case we come in contact with anything or crash. Hopefully most of our equipment will survive. We have some EMI and RFI solutions also, and like I said, we're transmitting at extremely high power, so usually if anybody's going to be having interference, it will be the other teams and not us. So we did this by using the 500 milliwatt video, and we're using 500 milliwatts on the data transmission also. And this gives us probably a 70 decibel wing margin. And you can see in the bottom left picture, this is actually one of the antennas we're using on the base station for the video. And this antenna has a fairly wide range, and it's fairly large, so that we get a pretty clear picture even when the vehicle is moving and inside of the building. Also, our next step was go ahead and testing each of the systems individually before we added them into the vehicle. Our vision team was able to run many tests, including interference tests and range testing, and we also bought a ton of LEDs and tried out different intensities of light, different frequencies of blinking, different shades of blue, and different colors also to see how robust our software was. For the navigation, the vehicle you see on the top right is what we call the micro mouse. And we set up a navigation system in 2 dimensions first. And this was actually done by our previous year's team in the past mission. And this was for the vehicle that actually would be propelled into the window and then drive navigating through the arena. And so we were able to set up our mission strategy on this vehicle. And you can see we've also added our camera to it so we could have a portable device. Our controls team, you can see in the bottom left picture, we have our yaw stand, and we performed many tests on the different stands, and before we did a tether test, which I do not have up here, but we also worked with the sensors too. Since these are ultrasonic sensors, there are all kinds of different issues you can run into having them on a vehicle, especially a flying vehicle. Some of these include the ground conditions, the prop wash, and interference between having the sensors close to each other, and any other kind of radio frequency interference or any kind of sound interference you may have. So we did test these. This graph shows under a fan at a high speed. This is under one of the props, and we were able to get a fairly consistent signal, but we did have outliers, so some filters will need to be applied. And in conclusion, this just kind of runs over what we've accomplished in the past year. We divided into 4 subgroups, and the micro aerial vehicle team designed the quadrotor, and then we tested the flight controller, and we also devised our mission strategy and tested this on the micro mouse. We chose our range sensors and came up with our vision recognition system and tested this also.